Hello everyone, my name is Ved, and today I'm here to present our research on automated make and model identification of reverse shoulder implants using deep learning methodology. Our aim and objective. Our aim is to build a convolutional neural network model that can accurately identify the make and model of a reverse shoulder implant. To this extent, our objective has been to build a robust and accurate model in order to achieve successful identification of the reverse shoulder implant with high accuracy. Our dataset consists of both anterior, posterior, and lateral images. AB images imply that the X-ray was taken from front to back, and lateral images imply that the X-ray had been taken from the sides. Our dataset consists of two different shoulder implants. The first one is the depoy delta, which consists of 20 images in AP and 10 images in lat. The second implant is the evolutus unique, which consists of 30 images in AP and 6 images in lat. Here are the X-ray images of the depoy delta implant. On the left is the AP view, on the right is the lat view. And here are the X-ray images of the evolutus unique implant. On the left is the AP view, and on the right is the lat view. The proposed approach. Our proposed work identifies make and model of two different reverse shoulder orthopedic implants from plain X-ray images using deep learning. The total amount of samples were divided into two different sets, training and testing, with a ratio of 70 to 30. The training images were used to train the model, and the testing images were used to determine the model's performance mimicking real world scenarios. The 70% of the training images were augmented using techniques such as random rotation and random zoom in order to increase the number and also in order to improve the model's capability. This was applied to both AP and LAT images together and also only to AP images as well. The proposed work compares the influence of different views, both AP and LAT together, in implant identification, thus making it the first benchmark performed in a shoulder implant identification study. The presence of only LAT images was not experimented on due to its very low quantity. Here, so the images are fed to the model in various batches. Here is what a single batch of training images looks like, both for both AP and LAT, and also for only AP on the right. After experimentation, here are the best obtained results for both AP and LAT images together in training. We experimented with three different powerful deep learning models: VGG16, VGG19, and Inception V3. All three of these models had been trained on the had been pre-trained on the ImageNet dataset in order to increase their efficiency and accuracy. These models were trained for 25 epochs, after which we got our results. EGG16 performed the best on the testing dataset with a testing loss of 0.2601 and a testing accuracy of 95%. Here are the best obtained results for only the AP images in training. VGG16 and VGG19 performed similarly with a testing loss of 0.3961 and 0.4125 respectively, and both had a testing accuracy of 86.67%. Inception V3 followed with a testing loss of 0.6775 and a testing accuracy of 80%. Here are the loss plot and confusion matrices for both AP and LAT images. If you look on the left, it is the training and testing loss graph, which implies that as our model was trained, the loss or the error decreased, which means that the model learned well on the images and improved its performance. Similarly, here's the loss plot and confusion matrix for only AP images. Our inference and the conclusions we derived from experimentation. Experiments were performed on both views of X-ray images, AP and LAT views, and also only with AP images alone for the classification of implants. All the proposed best results were then went through hyperparameter tuning, which involves tuning each deep learning model intensively with different hyperparameters such as learning rates and optimizers. This study leverages the optimizers such as ADAGRAD, ADAM, and SGD, which we'll explain in detail in the next slide. Each optimizer was combined with different learning rates. Learning rates is the rate at which the model learns. It must be balanced carefully after experimentation, because if the learning rate is too high, then the model overfits, and if it is too low, then the model underfits and does not learn efficiently. We experimented with values of zero point zero 0.01, 0.001, and 0.0001 for various epochs. After this, we found out that the Atom Optimizer was overfitting. It was performing well on the training dataset, but it had increased test loss. SGD, while it reduced the test loss, it failed to generate and enhance accuracy. Ultimately, Adograd gave us the best results with a good balance between accuracy and less overfitting. Our proposed novel framework identifies the make and model of the two reverse shoulder implants. What makes it the first of the kind is that it works with both AP and LAT view images and also only AP images. On both AP and LAT images, the VGG16 model achieved an accuracy of 95%, and on only the AP views, it achieved an accuracy of 86.67% in classification of the implants after rigorous fine tuning. With this, I want to propose our common solution. We are a team of orthopedic doctors, biomedical engineers, and computer science technologists across India, UK, the United States of America, Europe, and many such countries. We work to obtain a global solution for orthopedic implant identification since 2010. We have aimed to automate the entire process of implant identification across multiple joints such as knee, shoulder, etc. One such initiative by our team includes whichorthopedicimplant.com and unicornmedics.com. In these websites, the user can give the input X-ray image and can see what the make and model of the implant present from these X-ray images. Our study with the shoulder implants has also been hosted on a model which is available real time for doctors and the public to use at unicornmedics.com. Here is how the Which Orthopedic Implant website looks like. And this is how the Unicorn Medics website looks like. This website allows the model to work with real data. You can upload the X ray image of the shoulder implant you want, and the model will give you what the name of that implant is. This is our team: myself, Ved, Mr. Ramanathan A, Dr. Senthil, Dr. Malati C, Dr. Gayatri, Dr. Vineet Bhatta, our principal investigator, and Dr. Srinath Kamineni. For any questions and suggestions, please email us at ramsaivikbala at yahoo and dvedprakash2001 at gmail. Thank you so much.